So, now we will start module 3 of this course. In this module, I will be first finishing the part on vectors, where I will talk about vector integration. Then we will get to various elementary properties of matrices, including determinants, linear systems and Cramers rule. So, in the first lecture of this module, I will talk about line integrals and potential theory. Then in the second module, I will talk about surface and volume integrals, talk about Green's theorem and Stokes theorem very briefly. And then we will get to then I will start introducing matrices, talk about some basic matrix operations, and then a little bit about determinants. Then we will show how to solve a system of linear equations using determinants, what is known as the Cramers rule, and finally we will do some practice problems. So in this module there will be 5 lectures, and the 5th lecture will just be practice problems. So let us start. So today I will be talking mainly about line integrals and potential theory. So this is part of vector integration. And in vector integration, okay, there are 3 kinds of ways to integrate vectors. Now let's just step back a little. We will restrict this discussion to 3-dimensional space. Okay, so all this talk about line integrals, about surface integrals, and volume integrals will be restricted to vectors in a 3-dimensional space. Okay, so let's. Now, what do we want to do? As usually you have done things like integrating over some variable from some limits a to b of some function of x. So this is something that you are familiar with, and the way you are familiar with is that you think that this variable, if this variable x is shown like this, and f of x is some function which when you plot it looks like this, and this is point A and this is point B, then you know that this integral is nothing but the area under this graph between A and B. So, it is area under the function from A to B. So, area under function, okay, from A to B. So, that is what you mean by this integral over a function. Now, what do we have here? We have a function, but it is not a function of a scalar, rather it is a function of a vector. So, f of r, okay, and what we have to do is, what we are thinking of is something like an integral over a vector. So, what we want to think, this is a general idea of vector integration. Okay. This is the general idea of vector integration, that we want to do some sort of integral over a vector, okay. And now how do you put the limits, how do you define this? And as we are discussing that, we will come to line, surface and volume integrals very naturally, okay. So it turns out that you can think of different ways to integrate. Now you could have an integral just over a line, okay. So in this case your vector is something that points in 3 dimensions. So your R space, your R is a vector in 3 dimensions, okay, and now you are integrating a function of vector over various values of R, okay. So now this R can point in several different directions. For example, it can point this way, it can point this way, it can point this way, it can go in this direction. So all these are various possibilities for this vector R. And now what do you mean by integrating over a vector? That means you have to integrate over a range of values of R, okay. Now there are different ways to do it, okay. So if you integrate over a range of values of R, if you say your R can be anywhere in some region, okay, then you can have a volume integral. If you say your R has to be restricted to one line, then you get a line integral, okay. So what I want to emphasize is that depending on a range of values of R, we can have line, surface and volume integrals. Okay. So, depending on the range of values of r, you can have line, surface and volume integrals. So, for example, if I say that my r should be along r, whatever your r is, it should point along, it should be along this line. So, basically if you have r restricted to this line, then your r can be this, these are the allowed values of r. So, these green vectors are the allowed values of r that touch the line. If you imagine that you are allowing values of r to only take these values, okay, and you are doing an integral similar to what we did in the scalar case, okay, then you would get something called a line integral. Okay. On the other hand, suppose you say that in 3D space I have a surface, okay, I have some surface, okay, I will just call the surface S, and if my r can point to anywhere in that surface, any point on the surface, then I will get a surface integral. Okay. So, this would be something like a line integral, and this would be something like a surface integral. I have not told you how to do the integrals yet, we will come to that, okay, but just to motivate that depending on what are the allowed values of r. So, what you put in these limits, okay, you will get a line or a surface integral. Now, you could also have a case where you take some 3D region and you have some volume, and your r can point to anywhere inside this volume, it can point to anywhere inside this volume, then you will get a volume integral. Okay. So, you can get a line integral, a surface integral or a volume integral in this way, okay, and we will talk about this in today's lecture and the next lecture. Okay. So, now let us get to line integrals. Okay. Now, it turns out that that there is not just one way of defining line integrals, okay, there are a few different ways of defining. Okay, and ultimately we will stick to only one of them, but basically see, as I said, when we talk about functions of vectors, we talked about two kinds of functions. One was what are called as scalar fields and the others were vector fields. Okay. So, scalar field is, for example, you can have phi of x of r, which is equivalent to phi of x y z. Okay, that is a scalar field. Okay, and now how would you do an integral involving phi of x y z? We will come to that. Okay, you could also have something like a vector field v of r, okay, which has various components. I mean, each of the it will have 3 components, okay, and each of the components will be a function of x y z. Okay, so this will have vx of x y z, vy of x y z, and vz of x y z. Okay. So now there are some popular ways to define these line integrals, okay, and you know based on what your application is, you use the appropriate one. So one example, one way of defining the line integral is to just do an integral over a c. I will come to what c is. C is the contour of integration, contour or path of integration. And you can have something like a v, a vector field dotted into dr. Okay. Now, notice that since r is a vector, dr will also be a vector. Okay. And what we did is we took a vector field. This is a vector field. Okay, and you dot the vector field into dr, okay, because the vector field has various components. Okay, you dot these with the various components of dr. Okay, so this is the typical line integral that we will be talking about. Okay, so this is this. If you want, I can expand this out. Okay, so use dr equal to dx I plus dyj plus dzk. Okay. So this is a differential element in R. Okay. And if you have these as the components of the vector, I can write this as integral over c. Okay, c is a contour. Okay, and what I will have is Vx dx plus Vy dy plus Vz dz. So what you can write is, you can write it as a sum of 3 integrals. Each of them is an integral over a single variable. Each of them is integral over a scalar. Okay, so you have Vx dx, Vy dy, and Vz dz. Okay, so this is the typical line integral that we will be using. There are other line integrals where instead of a dot you put a cross, or you have a scalar field here, which I won't be talking about in this course, but you might come across those sometimes when you are reading various other books. Okay, but for this course we will just talk about this type of line integral. Okay. Now notice that since V is a vector, dr is a vector, V dot dr is a scalar. Okay, and so this is integral of a scalar. So what you get finally is a scalar. Okay, so this is a scalar. Okay, in other words, what you will get is a number. Okay, this integral, if you integrate over a contour and you put various limits, okay, then you will get a number. Now what is a contour? What is this contour? Contour has two things. Contour, so what you mean by this contour is some path. So if you take this as my space, so if I take this as x, y, z, okay, this is some path. Okay, it has some initial point and some final point, but the contour is not just specified by the initial and final points, it is also specified by the path. Okay, so contour is specified by both endpoints and path. Okay, this is a very important thing. When you are saying a line integral, it is not enough just to specify what are the limits, you have to specify the path. Okay, and we will come to this in a bit, and we will see when we actually do some examples of line integrals, we will come to this. So this is the definition of the line integral. Now where does the path enter? So the path actually specifies relation between x, y, and z, between the coordinates. So between this x, y, and z, the contour actually specifies this relation. Okay. Now we will come to the most popular example of vector integration is to calculate the work done by a force. Okay, and this is where we use the idea of line integrals. Okay, so we will do this. Okay, and we will take an example of calculating the work done by a force. Okay, what is it? So the idea is that suppose you have a force F. F is a vector field. It is a function of x, y, z. Okay, and due to this force, you displace a particle. You imagine that you have a particle that is moved by this force. Okay, then what is the work done? Then work. So if you displace it by some small amount dr. Okay, so this is displacement. So if you just move the particle a small distance, okay, dr, okay, then the work done is given by F dot dr. Okay, it is a dot product. Okay, and if you do over a path. So if you displace the particle some distance over some path, say let us say you go from point A to point B, okay, then the work done over some contour, we will call this contour C, then the work done is equal to integral over the contour C from A to B F dot dr. Okay, so it is just a line integral. Okay, I've just explicitly specified the endpoints, okay, A and B. Okay, so this is where this is the most common application of vector integration that you will see in chemistry. There are also many such examples in different areas of chemistry and also in engineering and other disciplines. Okay, now this, if you look at this picture right here, so you have A, you have B, and you have this path. Okay, so now this immediately raises a question that suppose I go from A to B this way. Now if I go from A to B by a different path, if I go this way, okay, is the work the same or different? So if I go through some path C1, okay, is the work same or different? Okay, so does work depend on path? Depend on path taken? And the answer is yes. In general, yes. Okay. Under some special conditions, you will have path independence, but in general, yes, it depends on path. Okay, and you will immediately recall when I say this, when I talk about path dependent work, and whether it is you will immediately recall from your thermodynamics courses. You talk about state functions, and you talk about transfer functions like heat and work, which actually depend on the path taken. So work is dependent on the path taken. Okay, under some special cases, it is independent of path. Okay, and we will come to that a little later. Okay, but before that, I will come to the example of the path dependence. Okay, so what we said is that the work dependent work done by a force, in general, it depends on the path taken. Okay, but I said that under some special cases, it is independent of path. Okay, so what is the condition for path dependence and path independence? Okay, so what is condition for path dependence / independence? Okay, so the question is, when is work path dependent and when is it path independent? Okay, and again this is something that you might be familiar with from your thermodynamics courses. So let us take again here we will take an example of 2D integration. Okay, so I'm just making this a little easier, okay, by taking a 2D integration. Okay, so for example, if you take f dot dr, okay, now this becomes fx of xy dx plus fy of xy dy. Okay, and now you want to ask a question. Okay, when is integral from a to b f dot dr independent of path? A to b. Okay, so when is it independent of path from A to B? Okay, now the way you can see this in many ways, but let me motivate it in the following way. Suppose I expand this out, so I have integral A to B. Now if I write this explicit expression for f, I have fx of xy dx plus fy of xy dy. Okay. Now suppose I could write this whole thing as, so suppose I could write this whole thing as so if this is equal to, if I could write this whole piece as something like dV, okay, I am using the term V, okay, from A to B, okay, then integral of dV is just V of B minus V of A, it's independent of path. Okay. So, if you could write your integral in this form, then it would be path independent. Okay. So, the condition for path independence is that you should be able to write f of x of x y dx plus f y of x y dy as dV. Okay. V is some field. Okay. So, V depends on x y z or x y, in this case we do not have z. So, V is a function of x y. So, if you could write it in that form, then it would be path independent. Okay. And the condition for this the condition when this is satisfied, okay, is when the partial derivative with respect to y of f of x is equal to partial derivative with respect to x of f of y of x y. So, what you do is you take the first f x of x y, you differentiate that with respect to y, that should be equal to f y of x y differentiated with respect to x. Okay, and these are partial derivatives. Okay, so this is a condition. So, if you have this condition, then this integral is independent of path and your work becomes independent of path. Okay, so now this is again a useful condition. You can always check whether your whether the work that you calculated is path independent or not using this way. Okay. However, let me mention one thing, that that when you say it is independent of path, that means you can take any path, okay, any path, and you will always get the same answer. Now, there are cases when integral might be same for two different paths, but it might not be same for other paths. Okay. So, even if it is path dependent, you might accidentally get the same work for two paths. Okay. So, that is also possible, but when you have this condition, when you satisfy this condition, it will be independent for any paths. Okay. So, let us quickly do one example of a line integral. So, here, okay, so what we are going to do is an example. Let us calculate the work done. So, if f of x y is equal to 1 over x square plus y square I plus 1 over x square plus y square j. Okay. What is the work being done going from a point so calculate work done in going from 1 1 to 2 2. Okay. And we'll do using two paths. Okay. So, the first path, okay, first path is you go from 1 1 to 2 1 along a straight line, and then you go to 2 2. Okay. And then the second path, so this is the first path. The second path is you go from 1 1 to 1 2 and then to 2 2. Okay. So just pictorially, what you have is you have the x and y. Okay. You have the points 1 1. So, this is 1 1, and here is a point 2 2. okay, and you do two paths. So in the first path you go from 1 1 to, just use two different colors. So the first path you go this way, in the second path you go this way. So this is 2, this is 1. So how do you calculate both these works? Okay. Now what you have to do is, in either case you will write that the work done. Okay. So let us calculate from path 1. Okay. So this is equal to integral. Now what you will do is you will write, you will multiply this by dr, and dr is dxi plus dyj. So what you will get is, you will get dx over x square plus y square plus integral dy over x square plus y square. Both are over path 1. I'll just put a 1 here. Okay. So these are the two things. Okay. Now you have to do both these integrals, okay, over path 1. Now if you can see, in path 1 there are two parts. In one part only the x changes, in the other part only the y changes. Okay. So in the first part of path 1, okay, in the first part of path 1 your dy is 0. Okay. In the second part of path 1 dx equal to 0. Okay. Not only that, in the first part of path 1, so in first part of path 1 dx not equal to 0, dy equal to 0 and y equal to 1. Okay. In second part of path 1 dx equal to 0, dy not equal to 0 and x is fixed at 2. Okay. So along the entire second part of path 1 x is fixed at 2. Okay. So this is the information about the contour that you have to use in order to do this integral. So when you put this condition you will get, so for the first part of part 1 dx is not equal to 0, so dy goes out. Okay. So all you have is, you have an integral over dx, the limits of x are from 1 to 2, okay, and you have x square and y is set at 1, so you have x square plus 1. So you just get an integral over a single variable, okay, and you can do this integral. In the second part what you have is integral dy, now y goes from 1 to 2, okay, now x is fixed at 2, so it is 4 plus y square, x is equal to 2, okay, and in the second part dx equal to 0, so that part goes away. Okay. So this is how you would get for the first part. So you can do both these integrals, okay, both these integrals are related to tan inverse. Okay. So this is nothing but equal to tan inverse, in this case it will be tan inverse of 2, in the second case it will be tan inverse of half. Okay. So it is a sum of these two is this. Now in the second part, in the second part you will get again very similar things. Okay. So but what will happen in that case is that in the first part your dx is 0, only dy is changing. So what you will get is integral dy over y square plus 1 from 1 to 2 plus dx over x square plus 4 from 1 to 2. Okay, and again this is the same, tan inverse of 2 plus tan inverse of half. Okay. So basically it is what you find is that the work is the same for both these parts, and in this case you can easily look at f of x y. Okay, you can look at both these and you can easily what you do is for these two parts you get the same work. Okay. So but is it path independent in general? The answer is not path independent in general. Okay. And why did I say it is not path dependent in general? You take d by dy of 1 over x square plus y square, okay, that is d by dy of this is not equal to d by dx of this, which is again 1 over x square plus y square. Clearly these two are not equal. Okay, you take a partial derivative of this and partial derivative of this, you will get different functions and they are not equal. So, in general it is not path independent, it is just for this special case of these two paths that you got path independence. Okay. So, in the next lecture I will talk about surface and volume integrals.